or are keeping track. The question is then, how do I get from the dynamic feedback we had in the previous talk to this, to feedback related to adding dynamic pattern matching with Python? And the best I can manage here is feedback doesn't just happen within our programs and within implementations. It also happens in the big space of language design. And well, at least I got a laugh from Stefan. So the point here is that, we know that these case statements invented by Tony Hoare, that's right, isn't it? Yes. Case statements were invented by Tony Hoare.
I don't know.
Case statements were invented by Tony Hoare, at least that's what he says. He says he made 2 contributions to programming languages. One of them was case statements, and we all know what the other one is. Null pointers, that's right. And then he was giving talks explaining how null pointers, were a $1 billion mistake that had crashed spaceships, and unlike parse errors, for example. Anyway, and so, object orientation came along, and I guess I'm an OR guy, Upsala, which has always been arguing that case statements, in fact, probably cost the industry more than null pointers, because they meant that your program was intrinsically non-extendable. If you want to add another case into the sum, basically, if you've got case statements, you're screwed. You've got to go through and modify your entire program. And once upon a time, Guido van Rossum obviously thought the same way, but I guess as things have gone on, and we can now see that expanded case statements and matching have been added to languages like Java and C# and even one called Grace, which really I don't have an excuse for. Sorry, Michael. And today, we don't have Guido, but we have Tobias, who says he's never physically met Guido, which is the same for most of us, I guess. I do wonder whether he still exists or whether he has just been replaced with a GPT-3 chatbot. And would we know the difference? But anyway, I'm sure Tobias has opinions on that. And he's going to tell us how he reintroduced the case statement into Python.
Kia ora, and thank you for having me here. Perhaps I can fill in the missing link here. So my research, my field of research is actually creating error messages in Python. And that means for a large part that I have to somehow analyze Python code. And kind of one of the things that I want to do as part of that, I get the AST and I want to simplify some of the things. So this is kind of a very simple thing that you're all familiar with. We have something like an addition in an addition, and I want to simplify that by adding the 2 numbers m and n. And here's the code that I have to write in Python, which is incredibly ugly. I mean, you've got all this checking, is the thing that I have here an instance of a binary operation, and is the left-hand side a binary operation 2, is the right-hand side a number, and so on. And what I wanted to do is to express this much more succinctly, more to the point of what's the structure of this entire thing. Well, if I have a binary operation with binary operation inside there, and both of them are additions, then let me kind of go and simplify that and spit out a smaller version of that. Now, you could think that perhaps I'm the only person in the universe that has this problem of handling kind of ASTs and all that, and having this huge if-instance statements. However, we actually checked when we did this pattern matching stuff and found that these 2 patterns here are very, very common in Python. The problem is Python is kind of, it doesn't have any types as kind of type guards as such. So you have no idea what type of the data is that you get in. So the first thing that you usually do is you check, is it instance of something, or do you have the attributes that you actually want to work with? Of course, you can write code with all that, without all that, and kind of it makes much more fun debugging that. So we have data in Python, particularly kind of that's non-uniform. Data is a kind of nested, recursive, hierarchical, or however you want to call it. And inside the data, you have some information that's hidden that you're actually after. On the other hand, you have pattern matching, which is a very neat way of dealing with polymorphic data structures and extracting the information that you really want. So that seems like a perfect match. Let's go and do pattern matching in Python to work with this data. And that's kind of the objective of what this project was all about. Adapt and integrate pattern matching with dynamic language Python. Here's the problem though. Pattern matching in its original form was really about algebraic data types. So the idea is that you have a kind of a very strict, exact structure of the data. You can access the different fields of the data. You know that if you have a binary operation kind of node, exactly what kind of fields it has and all that. However, if you look at object-oriented programming is about abstracting away. So if you have a good OOP design, the structure of the classes or the objects is hidden away. You can't just access it. And if you go to dynamic OOP like Python, it gets even worse because an object in Python, it has no guarantee that the attributes and fields that you're after are even there, or there might be kind of different attributes and fields. So we kind of try to marry two things here that somehow are conceptually on the opposite side of a spectrum between algebraic and abstract data types. So there's two things that I want to briefly discuss. First, let me just kind of briefly go over what is pattern matching in the first place, because pattern matching, and we've been trying to explain that over and over and over, is not case statements. So we didn't want to have switch and case statements in Python. We wanted to have pattern matching, which is about extracting information and not about having a fast switch table. The second thing then will be kind of more on what we did in Python specifically. So the objective of pattern matching is somehow to kind of filter the data that I get in and extract the relevant information out of that. Particularly, I assume that the data that I get in is organized in tree structures. In reality, it might be a graph that's kind of cyclic or whatever, but I just assume we have tree structures and I want to filter and extract the information of that. To give you just a very brief example, so I have a kind of very simple multiplication here. And this is how I would express that in the AST in Python. I have a binary operation node with a number and a name in it. And yeah, that's kind of how I write the thing. I will kind of stick to this, even though, I mean, pattern matching, you can easily come up with lots of different other examples, but that's where I came from, and I want to keep a kind of thread through the entire thing here. So with pattern matching, what I now want to do is I have this data up there, and I want to give you a template where I say, okay, I want to have this binary operation node, and in that template, I have two gaps, and that's kind of where the data that I'm looking after should fall through, and I want to bind that to two variables, x and y, to extract that information and work with that. Of course, an interesting case comes if I have more than one such possibility. So I do not know what's really the nature of the data that I get, and I can say, well, perhaps I have a unary operation or a binary operation node, and I have different parts of information I extract in each of these cases. And here's the syntax, how the exact same thing would look in Python, for instance. That's all kind of neat so far. But one of the things that we really kind of run into, just to give a brief glimpse in the design of that, is what do you really do with this name binding? So if you look at this example here, the question first is, what does case pi do? Let's assume pi is a constant from the math module. So should this case pi bind whatever value I plug in to a new variable pi, or should it compare the value to pi and succeed if it's the same? A bit more interesting even is if I have a tuple with xx, what does happen now? So if you look at the pattern, you would expect that I want to have tuples where both values are the same, or both objects are the same in one way or another. However, if you look at what Python does, if you take tuple unpacking or sequence iterable unpacking, the second case will always succeed, and you just bind the second value in the tuple to x and ignore the first binding. So it's really not clear what's happening here. So what we did in the first instance, because we really want to have pattern matching and not switch statements, it will bind whatever value you plug in to pi, to a new variable. The second case is something we outlawed. So if you want to compare a value to pi or do this kind of tuple of two equal values, this is how you would actually write it now in Python. The idea is that you only bind local variables, never kind of attributes or something like that. And the second thing is that you just get a tuple with two values, and then you have a guard where you say, okay, in that case, I want x and y to be the same, and if that's the case, you move forward. But that's kind of these cases have probably been one of the major battlegrounds with the Python community in trying to convince them that pattern matching, as we do it here, has a kind of meaningful application. And kind of a last thing to mention here is the problem is that Python's scoping rules is essentially that the only scopes that you can have is functions. So the scope that you have here is the entire function. So if you say kind of the second case xy, actually succeeds, it means that for the rest of the function, x and y are defined. So that's not kind of limited to this one case. And one of the reasons is that we kind of experiment with the idea of having functions here so that the scope of this x and y is limited. But that would mean that you couldn't use something like a return statement inside this case, or if you're in a loop, you couldn't use break and all that. So there's ramifications which make the entire thing worse. So just kind of to give you a little bit an insight in what kind of problems we had to discuss and solve during the design of pattern matching. So what is pattern matching? Just to summarize this part, we want to validate and check the data that we get in and see, is it really a binary operation? Is it a unary operation? Is it a tuple with two values? And if so, we extract information that we're really after and discard the rest. Second part. Now, let's talk about how do we account for dynamic objects. And the picture here is actually kind of chosen very deliberate, because we all know what a snowflake is. But the problem is, if you really look at the snowflake, it might be missing one of the arms or whatever. It's still a snowflake, but kind of might have a structure that's different to what we expect. And that's a problem what we might have in Python. So it might have additional or missing attributes or fields in your object, which make the entire thing much more interesting than if you just go with algebraic data types. So the challenge of matching objects, at least in Python, is twofold. First, we have no ordering of the attributes. They're just kind of, it's a hash table, essentially. So whereas in algebraic data types, you know, this is the first attribute, the second, and so on, we do not have any information like that. It's just a bunch of attributes. And the second, if you know the class of an object, that does not necessarily determine its structure. It gives you a good clue or hint that, yeah, probably this is what we could do with it, but there's no guarantee about it. So coming back to our example here, I started with this idea. I have a binary operation node, and I want to map these values to my binary operation template that I have here, and then x and y come out. And if you look at this picture here, it's pretty obvious what x and y should be. But if you kind of recall that we don't have this ordering of attributes, actually these are named attributes, and I just choose to order it this way. I could also have gone to operation left, right, for instance, rather than left, operation right or something. So I don't have the sorting, the order to really map it in a good way. The question is, what do I do then in order to make this work? And there's a number of solutions that we wanted to support. So here's an example of with binary operation. You could, for instance, have an additional field line number that I really do not care here about, and I don't want to kind of have to care about it if I do this pattern matching template. So first solution, I provide an explicit mapping, which means that I tell in my template, I name these different fields and say the first gap here is the attribute left, the middle one is the attribute OP, and the last one is the attribute right. So in syntax, that would look like that. So you see that it looks like named arguments here are not just giving the positional arguments as before. What's really ugly about this thing, even though it works and it's supported, is if you look at this item equals x, what's actually happening is that the variable x is bound to the value of item. So kind of this entire thing here is rather confusing, and you might spend some time wrapping your head around to what is happening here. Second solution is we somehow let the class decide how this mapping is going to work. So if I say my template here is binary operations, something, something, I say this binary binop class that should decide what attributes I then have. So in a way, I put the subject I want to match against into the class, and the class distributes it to the rest of the pattern that I specify. And that might look like this in Python. So I have here a passive solution where I just specify a tuple in my class that says which kind of what's the attributes names, the field names that I want to map if I have these positional gaps here. I could also go for a more active approach. This is similar to extractors in Scala, for instance, where I could say I want to have a method where I put in the subject, and the method is responsible for returning a tuple, and then I can kind of match the different things to my positional arguments. The very nice thing about this active approach here is, as you can see in the lower part here, that I could even expand on what I accept. This is probably a stupid example in why would you kind of want to accept the unary node as a binary node, because usually you want to differentiate between the two. But I really kind of want to stick to kind of this example here and show what's possible. But one of the examples, what you could do, for instance, is that you have two different classes for complex numbers, one rectangular and one polar, and depending on what you need, you kind of change the structure of the thing that comes in. So kind of these active patterns here are very, very powerful. We could even go a little bit further. So if we go back to this idea of, with an active pattern here, I put in the subject into the class here, as I've just shown before, and then I get back this tuple, these values that I distribute over the pattern. Perhaps I want to also put in a parameter. For instance, I could rewrite this binoculation thing and say, perhaps I really want to have a multiplication here, and then I just get out the two operands x and y. I will get to an example of why you want to do that in just a second. But here's kind of, for instance, how that might look in Python, where I use these square brackets to say, well, I want to have something that's given to the binop class and not something that comes out of it. And here's kind of one of the examples where we might use this parameterizing of the active patterns. Because if I just get some binary data, I do not know what the encoding of that is. but perhaps I might want to try different encodings, and then I have to feed in these encodings. Of course, you could go and write different classes for each of these cases, but I would argue that using kind of a parameter here is much more readable and elegant in the end. The main reason that we kind of considered this was actually regular expressions. Because if you do a regular expression match, you afterwards have to say, well, do you find any digits? Do you find any text? Do you find any something? And match against these things. So I have to give some kind of parameter or information to the class in order to allow it to determine whether it gives me back the tuple of information that I want or not. So to summarize, if you want to account for dynamic objects, I have to somehow explicit map from my subject to these positional arguments that I have in my pattern and kind of what kind of attributes do I want to get out? And I may ignore attributes that are not there. I might have to conjure up as some way of handling additional attributes, whatever. An alternative is to have this passive class-induced mapping, where just kind of the class specifies, hey, here's kind of the attributes that I expect, and I would extract. We could also go for a more active class-induced mapping, where I have this method that deconstructs my subject and then returns a tuple with the information, and I can even parameterize that. In the end, the first two kind of variants here are in Python 3.10, so we got that really into Python. If you're using a new version, that's in there. The thing is that there was a huge resistance from the community to make pattern matching too complex and kind of too powerful and all that. So the second half here, these active mappings or extractors or whatever, is something that's left for future work. And hopefully we kind of, as pattern matching gains in acceptance in the community, we can actually add that to Python as well at a later point. So with that, just a very brief glimpse into how pattern matching in Python, what kind of problems we had to solve and what we came up with, or kind of stole from languages that were better and more experienced. Thank you very much for your attention.
Hello. One of the big issues with writing maintainable, scalable code with this kind of tuple pattern matching is that you may get confused about which order the element come out on the tuple. In Python, we have named tuples that help us in that direction. I wonder if the pattern matching should allow you, for example, to extract in the variable called x, the field called x instead of the first field, no matter what, you know? If you could have like that, if you write .x instead of just x, you are talking about the named, you know, what you will get if you were to write .x or something like that. That will look like a very minor thing, you know, that you can add that could save impressive head edges. You know, if there was some way to ask for the decomposition to be nominal instead of positional, that's, you know, I will say it more formally.
So the first thing is just using x here to mean the field x is a problem, because we want it to be kind of fully nestable. So if I just have case x, I do not want to get the field x of the thing that I plug in, but the subject itself. So the question is how do you kind of work with that? And the second thing, we proposed or looked at stuff where you start with like dot field or something to make that happen. And there was kind of let's say, consensus from the community that Python has no example of such syntax up to this point, so that should not be introduced. So if you're kind of doing something like a heart operation on a living body, like Python, you have to be very careful that you do it in a way that you do not disturb kind of all the people's conception of how Python should look like or behave or whatever. So in the end, we had to find compromises and leave out many of the ideas that we
But
wanted.
they have named tuples, and the new data type things also tries to be a much more nominal approach to tuple composition and decomposition things. So there is clearly a lot in their community going on for having named-based decomposition. So I'm surprised that you found resistance to have name-based decomposition in this case.
Yeah. I mean, named tuples, to be honest, is something that never ever came up in our discussions. No one ever brought that up. So it was really more about kind of real objects in the sense of more general and how do we map these. Thanks very much.
Hello. Could you give us some insight regarding adoption in terms of the Python community kind of using pattern matching, and how do you sort of measure success?
I'm not sure I can measure success. Concerning the adoption, as I said, from all this feature, consensus was to a certain point that we want to have these basic pattern matching features in Python and now wait for kind of a couple of years and see what's the adoption and what kind of happens in the community with it. The problem is, of course, that this adoption, that will take a couple of more years. So just my Linux distribution is currently at Python 3.8, and we're kind of talking about 3.10 here. So I expect that in about 2 years, you could say pattern matching is really available across the band, and then it might start to actually be used. But at the moment, I mean, I wanted to have this feature in for my work, and I cannot yet use it because I cannot rely on that kind of the people who are executing my code have Python 3.10 or later. So I guess kind of that's really something that will take a couple of years in order to see what's really happening there. Just to kind of concerning success, one of the things that we also have to consider is there's so many people learning programming through Python right now and looking at Python and kind of coming from that into other languages, that having pattern matching in Python might, in the end, not be that feature that makes Python or that's regularly used in Python. But people might know, okay, that exists, and if they then switch to other languages like Scala or whatever, it's something like, oh, I've seen that. That's kind of something like a regular cool feature, and I'm using that. So measuring success in that sense is very difficult because we hope that it has ramifications beyond just being used in Python.
I have a comment directly about adoption. So I think the people you have to get about that is the teachers. So when I learned that the feature was available, I immediately forced my students to use 3.10 and subjected them to learn that just because I found the patterns that you showed initially so ugly. So the comment that I really wanted to make, you had this slide on binding, and I think that's, I mean, in Python, a variable never gets bound to a value. I'm just saying that, so you used it prominently, and that led me on a completely wrong trajectory. So in Python, whenever a new variable appears, it gets assigned. In Python, everything is assignment. That also explains this XX pattern. And therefore, to speak about declarative, you didn't say that, variable binding, that's not Python. So that's totally misleading. Everything that looks like a variable binding, be it that or be it, what is it again? Optional arguments. So if you have default values, if you think about that as something declarative, forget it. You're misled. Yeah? So always in Python, everything is assignment and of course dictionaries, and then you have understood everything.
Yes. Part of that is kind of adopting the lingua franca of pattern matching, of how you talk about that. And another part is, so we did go a little bit in that direction in that kind of the variables here are really kind of local variables. So you can't have global variables in that and things like that. So we try to kind of push it a bit in that direction, even though, as you say, yes, there's no declarative thing in Python. So yes, it's all assignment.
So I have a question regarding the implementation, because it seems that there might be two different ways to implement that. You can just regard it as a new language feature, so the interpreter has to do all kinds of, extracting data and doing the computation inside the case. The other option is maybe you can just desugar it into existing Python features, such as, using the ugly is instance of things like that. So how is that actually implemented in the new version?
Bit of both. So it's really a new implementation. So there are new bytecode instructions and all to facilitate pattern matching. We tried to be kind of as economical with introducing new really features as much as possible. But the thing is that some of the features that you would kind of immediately recognize here, we could not take from original Python, and that might be surprising. So for instance, Python already is iterable unpacking, and kind of we wanted to have that in pattern matching as well. But the thing is that iterable unpacking means that you change the state of your iterator because you go through the entire thing. If you have conditional pattern matching, that doesn't work because the pattern might fail and then you have to go back to where you started. So in that case, we had to kind of change the implementation of what's already there with iterable unpacking and come up with something that's only looking at sequences, for instance. So there's kind of additional checks here really to make sure that it works in a conditional case without changing the state. So yeah, it tried to be more or less desugaring, but we had to kind of make some concessions there to account for these new cases.
I understand that at some point there will be a reception and drinks for which you should have a ticket in the lobby. There is also a student research competition. Have you got anything more from? Yeah. And Stefan has more DLS stuff.
Yeah, putting my other hat on as a steering committee chair. So thank you all for coming. I see an almost full house, great. As you have noticed, there were not a lot of submissions. So I hope everybody seems to be interested in dynamic languages again. A revived interest after COVID, as it seems. So I hope to see many of you to submit to DLS in Lisbon next year. Might be a little bit less far for many to travel. But yeah, so we will be co-locating with Splash again and looking, of course, for submissions. Otherwise, I would like to thank, of course, the original organizers, Wolf and Arjun, our program committee, and all the speakers today. And yeah, that's it. Hope to see you next year.